Now we will again revisit the matrix transpose properties, and we will do some more questions on that. So the first property is, as mentioned before, if we take the transpose of a matrix, we will get the original matrix A. The second property is if we are adding two matrices and then taking the transpose, that's the same as the first. We take the transpose of the first matrix and then take the transpose of the other matrix and then add the both matrices. So the third property is k. If you have scalar k times a matrix and then you are taking the transpose, it's the same as k times the transpose of the matrix. So this is true for every scalar. Fourth property is if you are multiplying a and b and then taking the transpose, it is equivalent to say that first you take the transpose of matrix B and then the transpose of matrix A and then multiplying in this order such that B transpose is first and A transpose is on the right. Here is an example. So in this example, you are given a matrix A and a matrix B. You have to verify the last property. So the last property is A times B whole transpose is the same as B transpose times A transpose. Okay, so in the solution, we will prove the last property that A times B whole transpose is B transpose times A transpose. So in order to prove this thing, we will first compute the left hand side and then we will compute the right hand side. Okay? So put the value of A first and then put the value of B and then take the transpose. So first of all, we will multiply these two matrices. So first I will multiply first row with the first column. It will be 1 times 0 plus 2 times 1. And then with the first row with the second column, which is 1 times 1 plus 2 times 0. And then we will go to the second row and the first column, which is 3 times 0 plus 4 times 1. And then second row with the second column, which is 3 times 1 plus 4 times 0. And then transpose is as it is. So this is 2 and this is 1, this is 4 and this is 3. Now you have to take the transpose. If you take the transpose, this row will become the first column and then this row will become the second column. Okay, so this is the left hand side. Now you will take the right hand side. So the right hand side is B transpose times A transpose. So what is B? B is 0, 1, 1, 0 and we have to take its transpose times what is A? A is 1, 2, 3 and 4 and its transpose. So first we will take the transpose of B. So I will write this row as a first column and the second row as a second column. And similarly, I will apply the transpose here on A also. So first I will write the first row as a first column and then the second row as a second column. Now transposes are applied. Now we have to multiply these two matrices. So first I will multiply the first row with the first column. So 0 times 1 plus 1 times 2 and then first row with the second column, which is 0 times 3 plus 1 times 4. Then second row with the first column, which is 1 times 1 plus 0 times 2. And then second row with the second column, which is 1 times 3 plus 0 times 4. If you just simplify these calculations, you will get 2, 4, 1 and 3, which is the same as you got from the left hand side. So you can easily say that left hand side is equal to the right hand side. Since left hand side is equal to the right hand side, so the property is verified. And this is done. So another exercise is to verify all of the properties which I have mentioned here. These are three properties. The fourth one I have proved. So you can prove the first two properties in general, and this property for k is equal to, for example, 3. Okay, so you can easily prove all of these properties for any specific value of k. So you can do that. Now we will move to the next part. So the next part is the theorem. The theorem says for any matrix A, the matrix A times A transpose is always symmetric. Also, A transpose times A is also symmetric. So this is the theorem which we have to prove. So here is the proof. I will prove the first part. So I will prove that A times A transpose is symmetric. Okay, here is the definition of symmetric matrix. The matrix X is symmetric if X transpose is equal to X. Here is the definition. It is just for you to recall if you don't know. So I have to prove that this is symmetric. So assume that this is X. So if I will show that this is symmetric, so what I will do, I will take its transpose and I will expect to get the same matrix back. Okay? So in order to show that A times A transpose symmetric, we will take the transpose of A times A transpose, and we will check that whether A times A transpose whole transpose is what? Either it is the same matrix like A times A transpose or any other matrix. So let's check. So A times A transpose. So we will take the transpose of this matrix. So if you take the transpose of this matrix, so this is first matrix, this is the second matrix. If you have two matrices, for example, X and Y, and you have the transpose, you will write Y transpose then X transpose. So this is the fourth property you check. That is with A and B. So I have written with X and Y. So what will I do? So this is your Y and this is your X. So what will you do? You will write Y first and you will take the transpose of Y. So I will write the transpose of Y. times you will write x and then write its transpose. What is x? X is A. Okay? So I will write A transpose. So what is this? A transpose whole transpose. By the first property, it is A. And what is this? This is A transpose. Okay, let's look it back. A transpose whole transpose is the same as A times A transpose. So that means A times A transpose is a matrix. If you take its transpose, it will be unchanged. There is no change after taking the transpose. So that means it is symmetric. So, the second part of this theorem can be proved similarly. So for the second part, you will take the transpose of this and you will get this matrix back. So which means that this is also symmetric.